Hi guys, welcome back to Physics 101, the series in which we're covering complete overall physics syllabus. And this is the part 2 for the chapter 1 kinematics. In the last part, we talked about distance, displacement, velocity, speed, and displacement time graph, distance time graph in various cases. And in this video, we're going to be looking at the acceleration of free fall, which is acceleration due to gravitational force, and in it we're going to be learning about the effect of air resistance, and we're going to be also talking about the terminal velocity. And at the end we're going to be doing one or two practice questions to cover up the things which we have not, and also learn how to solve a question. So let us begin with the acceleration of free fall. Now this is a very common phenomenon and all of us experience it. If you're holding a ball in your hand and you lose the grip of it, it would come down and fall to the ground. Now this falling down is due to gravitational force and it makes it come down, and as it comes down its speed increases, which means it accelerates, and this acceleration is constant, and actually this is 9.81 meters per second square, but in O level while calculating we use 10 meters per second square, and this is perfectly acceptable as, and the answer are considered correct for this 10 meters per second square. So it will accelerate, and acceleration, the direction of the acceleration will be towards the center of Earth. Now this acceleration is not affected by the mass of the object. So how do we know? Let us consider a case that we have, let's say, a feather. It's not looking like a feather, but let's suppose this is a feather, and we have a heavy small steel ball, very heavy, and we have placed both of them in a vacuum. So let's say there is a chamber which is, and there is no air in which, and this is, let's say, a vacuum, and if we leave both of them at the same time, they would come down at the same time, which means they will move with the same velocity. Their velocity increase in velocity would be same, and they will fall down at the same time, which means that they accelerated at same rate. So which gives us conclusion that this acceleration is not affected by the mass of the object, but rather it is constant. Now looking into the real scenario, one thing, air resistance has a very great effect on this. For example, if you have a leaf, or again let us take feather for example, you have a feather and you're in the atmosphere, in the air, and you leave this feather, its speed does not increase uniformly, rather it increases, then it increases at a lower rate, then again a point comes where its speed gets constant, and then there is no acceleration. That point where there is no acceleration and the speed gets constant, that is the terminal velocity. Now one thing that comes from this case, that air resistance increases with speed. Now you would have experienced air resistance when you're cycling or running. You see that air actually opposes your motion, and as your speed increases, the air resistance also increases. This is the one thing. So as it is coming down due to acceleration, its speed is increasing, but the air resistance is also increasing, and a point come where the speed of this feather becomes equal to the air resistance, so that it is no more accelerating. There's no net force on it, so it is moving at a constant uh, velocity. So if we plot a graph of it, it will look something like this. Speed increases and then slowly it decreases and then it becomes constant. Now, one case which is frequently asked in the questions and you should have a great grip on is the case of a falling parachutist. Now, when a parachutist uh, of a base jumper, let's say a guy jumped from an aeroplane, what would happen is because of the acceleration which it feels, which it will experience, its speed will increase. But as the speed increases, the air resistance is also increasing, which means uh, its acceleration should slowly decrease, and a point should come where its speed becomes constant, which is actually the area of the terminal velocity. Now, in terminal velocity, the speed of the uh, guy coming down is equal to that provided by the air resistance, the resistance provided by the air resistance. So it has no net force and it moves in a constant speed. Now he opens up the parachute, let's say, then it will have like great decrease in its speed, a very steep increase in its speed, decrease in its speed it will face, and then it will again reach terminal velocity at a point. With these topics, but one thing which I missed in the last video was how velocity can be negative. As you know that the velocity is basically a vector quantity, which means that it has a specific direction. So if an object moves in from A to B and the displacement is x and the object is moving with a velocity of v meters per second. Now with the same speed, if it comes back, its velocity will no longer remain v meters per second, but it would then be negative v meters per second. So object's velocity becomes negative if it travels in the opposite direction. Let us do some practice questions. Now let us begin with this question over here, which shows us a graph, a speed time graph, and is asking for the average speed of the car during the first 3 seconds. Now average speed is basically total distance divided by total time, as we have discussed in part 1. Now one thing which we did not discuss was that the area under the graph, area under the speed time graph actually represents the distance covered by the graph. So this thing you should not forget. Area under speed time graph basically tells us the distance covered by the moving body, and the area under the velocity time graph tells us the displacement covered by the body. What is the average speed of the car during the first 3 seconds? And the graph is only limited to 3 seconds. So first of all, we would have to find the total distance, and total distance is actually the area under the graph. And if you look, the area under the graph over here is basically the shape of a triangle, and you know the formula for the finding the area of the triangle is half base into height. So over here the base is 3, so we calculated like half into base, which is 3, and height over here is 12. So we over here have the distance covered by the car is as 18 meters, and meters as the unit over here is meters per second, and the time over here is 3 seconds, so we basically divided with 3. So average speed over here would be 18 divided by 3, that is equal to 6 meters per second, which over here is part option B. And so this is the correct option. Now the second question says that a car takes 1 hour to travel 100 kilometers along a main road, and then half hour to travel 20 kilometers uh, along a side road. What is the average speed? Again, average speed has been asked. Now average speed is total distance over total time. The total distance over here would be 100 plus these 20, which would be 120 kilometers, and the total time would be half hour plus this 1 hour, that would be 1.5 hour, and the answer which we would get over here would be 80 kilometers per hour. Now let us do this P2 question. The question states that compare the sizes of and the directions of the two forces. Now force B is the force in which the is in the direction in which the car is moving, so it must be the driving force, while force A is opposing the direction of the movement of car, which means that this should be a resistive force. That could be like friction of road, air resistance, etc. Now compare the size and direction when it is moving at a constant speed. Now at constant speed and rest is possible when the force is are balanced and there is no net force. So if force B gets equal to force A, then there would be no net force and hence there would be no acceleration, so either it would be at rest or constant speed. So A and B should be equal first of all, and of course they should be in opposite direction as they are. In part 2 they are asking for comparison when the car is accelerating. The car will accelerate if force B is greater than force A, so there is more force in the forward direction, so it would accelerate. If force A gets greater than force B, then the car would decelerate, but they are asking for acceleration, so we have to mention that force B should be greater than A, and of course there is again in opposite direction. Suggest the direction of the resultant force on the car when the car turns at a corner at constant speed. Now one thing you must know is that in any motion of a circle, whether a car is turning, an aeroplane is turning, or any other circular motion or curve motion, even if an object has constant speed, it will accelerate, as you know, and the direction of the acceleration would be towards the center, so that direction of acceleration in any curve is or circle is actually towards the center of circle. So here we have to write that the direction of the resultant force, and then the direction of resultant force will also be towards the center of the circle, and as acceleration would also be towards the center of circle. As when the car would turn, it would form kind of a curved path. Figure 9.2 shows the speed time graph for the first 24 seconds of the motion of along a straight road of the car along a straight road, and during this motion there is a period of uniform acceleration. Now this is a speed time graph and they're talking about the acceleration, so we must know that when the gradient of the speed time graph or velocity time graph represents acceleration, and they're asking about uniform acceleration. So uniform acceleration would be where the gradient is actually the same. Gradient does not change, it remains uniform, and the gradient is constant from where the line remains straight, and that is I think till this point, which is actually at 8 seconds, and this line starts at 0 seconds. So we write the start and end points, so we can just simply write 0 and 8. And then they ask, state the main energy changes that occur in the 24 seconds. Now during the whole journey, of course, let's say the car is run on petrol or diesel, we have to write what happens is actually the chemical energy stored in that changes into kinetic energy that makes the car move. And with that kinetic energy, there are also some losses because of the friction and air resistance. There are some losses in the forms of heat. So we'll write over here that chemical energy, you can also write electrical energy as there are also electric cars. So you write chemical energy is changed into kinetic energy plus loss, like energy loss such as heat. Calculate the acceleration of the car during the first 5 seconds. State clearly the equation that you use. First of all, let us talk about equation which we use. So state the acceleration of the car during the first 5 seconds. Now looking at the graph, we have to actually we can from here see the change in speed, and we have time. So simply we will use the main equation, which is change in velocity over time. This is the equation which we'll use. So the acceleration from 0 to 5, which would be somewhere around over here, change from actually 0 meters per second to going, which goes up to like 8, because this is the point of 5 seconds, and where speed is actually 8. So we can simply change velocity 0 to 8, so change would be 8 minus 0, and the time is 5. So 8 divided by 5, that would be 1.6 meters per second squared, and that is the acceleration in the first 5 seconds. Determine the distance traveled in the first 5 seconds. The distance is calculated from a speed time graph through the area under the graph, as the area under the graph of speed time represents the distance traveled. So over here they're asking about the area, the distance traveled in first 5 seconds. So we have to simply look at the shape, which is area is calculated 1 by 2 into base 2, height base is 5, height is 8, and that is, I think, will give us 20, I guess, 20 meters. The next part states the car is stopped by applying the brakes. Various factors can affect the distance traveled by the car during the time that the brakes are applied. Apart from the forces applied by the brakes, state two of these factors. Now, when you push on the brakes, the tires stop rolling, and the friction between the road and the tire makes it stop. So, if there is less friction, then of course the car can be affected, the braking distance can be affected. uh, Now either it can be affected if you have, let's say, wet road. So condition of wet road would make it difficult to brake. You right, condition of road also, if your tires are worn out, they become plain with the passage of time. So of course that would also affect. So you right, like condition of tires. Now another effect is, although you have to just write two, but let us discuss another one. Now there is a thing called inertia, which is actually the Newton's first law of motion, which states that if a body is moving, it will continue to move, or if it is at rest, it will stay at rest until or unless an external force is applied. So a mass actually resists in a change in its state of motion. And if the mass is greater, the greater will be the resistance. So if the mass of a car would be greater, then what would happen is it would give a greater resistance to being stopped, and hence the braking distance will increase. So what how can the mass increase? Is one way that the mass could be increased is by the number of passengers. So that is actually also a point which could affect braking. More number of passengers, the difficult becomes to brake. So this was it. We have discussed a few questions and we have also covered the whole topic. If you have any queries, please comment down below and I would be more than happy to answer. I hope you learned something. Thanks for watching.